The goal of this video will be to prove the following theorem, which connects category theory to linear algebra, and which says that in the category of vector spaces over a field K, a morphism is monic if and only if it's an equalizer morphism. So this is an if and only if statement, but we actually only need to prove this direction going forward because any equalizer morphism is already monic. We know that from the video on equalizers. So all we need to prove is the forward direction. So we have to prove that any monic morphism in the category of vector spaces is an equalizer morphism as well. And what is a monic morphism in the category of vector spaces? Well, it's an injective linear transformation, right? Morphisms in Vect K are linear transformations, and it's monic, which means, since it's kind of like a set function, that it's going to be an injective function. So we have, suppose that our linear transformation T, maybe going from V to W, is an injective linear transformation. So let's draw that here. Suppose we have some T going from V into W. We need to show that T is also an equalizer morphism. So what does that mean? That means that the pair VT forms a limit over some diagram with two parallel morphisms in it, right? So we have to find some pair of morphisms going from W into some other vector space over K. So we don't know what these are yet. And not only that, such that T followed by this morphism commutes with T followed by this morphism, and for any other linear transformation X, say maybe going from U into W, which also makes those two commute. So if X followed by this one also commutes with X followed by this one, then we need to find a unique mediating morphism, theta, going from U into V, such that this triangle here commutes. So that's X equals T after theta. So this is quite a general statement that we have here. There's not a lot to work with in order to try to find our two parallel linear transformations here. All we know is that we have a linear transformation between two vector spaces, which is injective or monic. Well, one thing we know is that the image of T in W is going to be a subspace of W, right? So if we have the full image of T here, where we applied to all of V, then we get a subspace of W. And we've also seen in a previous video that we can take the quotient space of any vector space over one of its subspaces, right? So we could define W over T of V, which is the quotient space, and it's also a space over the same field K, since T of V is a subspace of W, where this is the equivalence classes formed by the cosets of T of V, and we know that if we take W over T of V, the quotient space, to be the codomain here, then we do have parallel linear transformations. One is the zero linear transformation, and the other one is the canonical projection from the vector space into its quotient space. So let's write that out. We have the zero linear transformation going from W into the quotient over T of V. That one's pretty simple. We just take any W in W, and we assign it to the equivalence class 0 or 0 plus T of V. These are the same way of writing the same thing. This is the equivalence class of 0 in this quotient space, and this is the coset of T of V with the 0 vector. And this other linear transformation pi, also going from W into the quotient space, is just defined by the canonical projection, right? It just projects W into the equivalence class of W in the quotient space, or we could write it as W plus T of V, the coset of T of V with W. Now, are these both linear? Yes, they are, right? This one is trivially linear. You can prove that to yourself if you want. And this one we saw in a previous video forms a linear transformation, this canonical projection into a quotient space. So we have two parallel linear transformations with W as their domain, which is exactly what we needed. So we found the parallel morphisms, Z and pi, but now we need to show that T, or the pair V and T together, form an equalizer over this diagram here, the diagram with Z and pi in it. So we have the parallel linear transformations, but we need to show that T right equalizes Z and pi, or that T followed by Z commutes with T followed by pi, right? That's the first property in order for it to be an equalizer. So we have that because 0 applied to T of V for any V in V is going to be equal to just the equivalence class of 0, right? It doesn't matter what T of V maps to. 0 is just going to squash it all back down to 0, basically. And this is 0 plus T of V. But that's just equal to any T of V in W projected by the canonical projection, right? It doesn't matter what T of V is. If I project it, it's going to be in this coset, right? It's 0 plus T of V. So it's 0 plus all of the values in T of V. So we get, based on this, that Z after T is the same thing as pi after T, which is exactly what we needed for the first condition for an equalizer. These commute. So now we need to show this mediating morphism property here. So let's suppose that UX as a pair forms another cone over the diagram containing Z and pi. What does that mean? Well, that means that X followed by Z also commutes with X followed by pi, just like T did. So that is Z after XU is going to be equal to pi after XU for all U and U. And if that's the case, well, this side is equal to the equivalence class of 0, right? For the same reason, we're just, whatever this is, we just squash it with the 0 linear transformation. And then, so this is pi after XU on this side. And what is this saying? Well, this is saying that anything in XU, when projected, ends up in the 0 equivalence class. X of U is in the kernel of pi, right? XU is part of the vectors that get mapped to 0 by the canonical projection. And what is the kernel of pi? T of V, right? It's exactly the cosets of T of V, so the things that get mapped to 0 are all of the things that are in T of V already. We don't need to add anything to them. 0 plus T of V. But remember, this was for any U, for all U and U. So basically what this is saying is all of the XUs land in T of V. And the XUs together form a subspace, right? For the same reason as we said earlier, it's like the image space. So X of U is a subspace of T of V. Both of them are image spaces. And if that's the case, then for all U in U, we have a V in V such that X after U, or X of U, is T of V, right? Because they're all contained within T of V. But remember, T is injective. So that means for any of these XUs, there's only going to be one V that maps to that specific XU. So we can actually say that for any U in U, there's a unique V in V such that XU equals TV. But for all U, there exists a unique V means we can define a function, right? So let's define a function K going from U into V, and it's defined by K of U is the unique, this is equal to the unique V in V such that XU equals T of V. And if that's the case, then you can just plug in K of U into this formula, right? So this is basically K of U here. So you get that T of K of U is equal to X of U. And if that's the case, then you get that T after K is equal to X. And that's the exact commutativity triangle that we needed here. So we have found a potential mediating morphism, K here, but what do we need to show next? That it's unique, right? It's the only morphism, or it's the only linear transformation that allows these to commute. So suppose there's some K prime such that T after K prime is equal to X. Well, X is equal to T after K. So we get T after K prime is equal to T after K. But T is monic, right? It's a monic linear transformation. So we can cancel T on the left. And we get that K prime is equal to K, which is what we needed, right? So we know that this K is the unique mediating morphism that makes this triangle commute. So basically, we've found our theta, which is K. And so the three boxed expressions together mean that the pair VT is an equalizer for the diagram containing Z and pi. Or that is that T is an equalizer morphism, which is what we needed to prove. And so this is a good example of a time of how category theory can be helpful, right? We looked at T as both injective here when we wanted to say that for every U, this V had to be unique, right? We used it in the regular set theoretical way of thinking about injective. Or we can use it as left cancelable, right? Because it's monic. So this is sort of the non-categorical application, and this is the categorical application of the fact that T is monic. Now that's it for the proof, but I haven't written QED yet, and there's a good reason for that, which is that we've skipped a very important step in the proof. And so we're going to need to go and patch that up. So the question is, what did we miss? Maybe pause the video here. What did we miss in our proof so far? And why can we not call this proof complete? And the answer is, well, we defined this K here, and we know that it's a well-defined function thanks to this property. And it helped us to complete our commutativity diagram here. But we don't know if it's a valid morphism in Vect K. What does it need to be a valid morphism in Vect K? Well, it needs to be a function, which we know, and it needs to be linear. So we need to still show that K is a linear transformation. Otherwise, it's not even in this category, so it certainly won't satisfy this definition. If you want a bit of a trickier exercise, you can try to prove that yourself. Try to show that K is linear. And so in order to do that, we need to show that K preserves addition and K preserves scalar multiplication where the scalar comes from the field K. And to do that, we're going to use the fact that T is monic once again. So it's like a third application of the fact that T is monic. And so we're going to remind ourselves that if TV1 equals TV2 for V1, V2, and V, then it must be the case that V1 equals V2. Right? That's just the definition of injective. And so let's look at T K U1 plus U2. Well, remember that this formula can be rewritten as XU equals T KU. And so this can be rewritten as X of U1 plus U2. But X is linear. So this is XU1 plus XU2. And then we can reapply this formula again to get that this is TKU1 plus TKU2. And T is linear. So we get TKU1 plus KU2. And so we can apply this formula, right? Or this statement here. So we have this expression is equal to this expression, and they're both T in front. So that means that the inside expressions must be equal, which is KU1 plus U2 is equal to KU1 plus KU2. And so we have preservation of addition. That's the first check. And similarly, if T of K of C times U, where C is some constant scalar in the field K, then we have by this formula that this is X of C times U. And then if this is the case, well then X is linear, so we get C X of U, and then reapply this formula to get C T K of U. And if that's the case, then T is linear, so we can move the C inside, and we get T of C times K of U. And so we get the same application of this statement here. So the insides here must be equal, and we get that K of C times U is equal to C times K of U. And that's the second check, so it preserves scalar multiplication. And so we're good. K is a valid linear transformation in Vect K, and so it can serve as our mediating morphism, our unique mediating morphism, as we found earlier. So that is QED this time. So to sum up, any linear transformation T from a vector space V to a vector space W, which is injective, is also an equalizer when you take it together with its domain, say V, for the diagram containing the zero morphism or the zero linear transformation and the canonical projection from the codomain W into the quotient space W over T of V. And so any monic linear transformation in Vect K is an equalizer morphism, and vice versa is also true, so this has been proved.